Pluto was supposed to be finished, a frozen dwarf planet, demoted and drifting at the edge of the solar system. Then the James Webb Space Telescope studied it in mid-infrared light, and according to recent analysis, what came back did not match the old story of a lonely ice ball. Webb's data point to something stranger, a high-altitude haze that does real work, a climate system unlike anything else we have seen in our solar system, and behavior so unusual that scientists are describing Pluto as a new kind of climate laboratory. Here is the first surprise, and it arrives fast. It is not a mountain, not a crater, not some dramatic new surface scar. It is Pluto's atmosphere itself. Webb's mid-infrared observations help confirm that Pluto's famous haze is not just pretty fog floating in the dark. Those tiny particles help cool the upper atmosphere. They reshape how heat moves. They help explain why Pluto's air is colder than models once expected. In other words, Pluto is running a climate engine, and that engine looks different from Earth's, different from Mars, different from the giant planets. That is the early payoff. Now the deeper mystery opens, because once you accept that Pluto has an active climate identity, you have to ask a harder question. How did we miss this for so long, and what else is still unresolved out there? To understand why this moment hit so hard, go back to what Pluto used to mean. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet. That decision still stings for a lot of people. It also stuck a label on Pluto that felt smaller and quieter. But labels do not control physics. Even after the demotion, Pluto remained one of the most interesting worlds we have ever visited. Then, in 2015, NASA's New Horizons spacecraft flew past it and rewired public imagination. Suddenly, Pluto had mountains of ice, a heart-shaped plain of nitrogen ice, blue hazes in the sky, and a surface that looked young in places, sculpted by processes that should not have been possible on a dead world. People fell in love with Pluto again. Scientists did too. But New Horizons also left an unfinished sentence. A flyby is brilliant and brutal at the same time. It gives you a flood of data, then it is gone. New Horizons gave us astonishing images and critical atmospheric measurements during its brief encounter. It showed that Pluto's atmosphere is thin, nitrogen-rich, and layered with haze. It revealed that sunlight and chemistry can cook simple molecules into complex organic particles high above the surface. That was already a revolution. Still, there were questions a single pass could not settle. How does that haze actually control temperature? How does the atmosphere behave across wavelengths that could not be fully probed at the time? How much of Pluto's climate is driven by particles rather than gases alone? And what does that mean for the whole Pluto-Charon system over long seasonal cycles? Those questions waited. Then Webb arrived with a different kind of vision. The James Webb Space Telescope is built for infrared light. That matters because infrared is where cold objects and atmospheric processes can reveal their thermal fingerprints. When Webb turned toward Pluto and studied it in mid-infrared wavelengths, it was not just taking a prettier photo, it was measuring energy. It was testing climate models against real thermal behavior, and based on current interpretations of that work, including analyses highlighted by university teams and science outlets in 2025, Webb's data strongly support a remarkable idea. Pluto's high-altitude haze is a key driver of its climate, not a side effect, a control knob. Think about how unusual that is. On Earth, we talk about greenhouse gases, clouds, oceans, and the way sunlight and infrared radiation move through a thick atmosphere. On Mars, we talk about a thin carbon dioxide envelope and dust. On Titan, we talk about organic haze and a dense nitrogen atmosphere under a different chemistry. Pluto is colder, smaller, and farther out. Its air is incredibly thin by Earth standards. And yet, that thin air is not simple. Ultraviolet light from the sun breaks down nitrogen and methane high above the surface. Those fragments recombine into heavier organic molecules. Those molecules clump into haze particles. The particles can absorb and scatter light. They can radiate heat. They can change the energy balance of the upper atmosphere. Webb's mid-infrared observations helped lock in the interpretation that this haze is actively cooling Pluto's atmosphere. That is the concrete finding, not a rumor, not a thumbnail claim. A climate process made clearer than ever, and that leads to the part that really shocks people once they sit with it. Pluto may be colder because of its own atmosphere, not warmer, cooler. That flips an instinct a lot of us carry from Earth. We hear atmosphere and think insulation, we think greenhouse, we think heat trapped. Pluto shows another path. In its upper atmosphere, haze particles can radiate energy away efficiently enough to lower temperatures below what older models expected. That forces scientists to rethink how thin atmospheres work at the edge of the solar system. It also means Pluto is not a passive ice ball with decorative fog. It is a world where chemistry, sunlight, and particle physics team up to set the thermal rules. This is where online conversation often goes sideways. You may have seen videos claiming James Webb discovered a brand new world hidden near Pluto, as if a secret planet just popped out of the dark. That kind of headline travels fast because it sounds huge, but careful science communication requires a clear line. Webb did not confirm a previously unknown planet parked next to Pluto. The verified, high-value result from recent Webb-era work is about climate, about haze, about thermal behavior, about a small world with atmospheric physics that look unique. Speculation about faint objects, unresolved neighbors, or mysterious detections can grow around real excitement, especially when people are hungry for the next New Horizons level revelation. Some of that chatter is pure hype. Some of it is people extrapolating from incomplete ideas about the Kuiper belt, orbital dynamics, and how much of Pluto's environment remains poorly mapped. The responsible takeaway is this: Pluto's neighborhood is still full of open questions. The Kuiper belt still holds undiscovered objects. But the shock that holds up under scrutiny right now is not a secret planet sticker. It is the realization that Pluto itself behaves like a climate laboratory we barely understood. Even without inventing a new world, the Pluto system is already weird enough. Pluto and Charon are not a simple planet and moon pair in the classic sense. Charon is enormous relative to Pluto. They are often described as a double system, locked in a gravitational dance where the barycenter, the balance point of their mutual orbit, sits outside Pluto. That alone makes the system special. Add in smaller moons, long seasons, and extreme orbital distance from the Sun, and you get a machine that changes slowly but dramatically over decades and centuries. When Pluto is closer to the Sun, more of its surface ices can sublimate into the atmosphere. Nitrogen and methane can rise, chemistry accelerates, haze production can shift. When Pluto swings farther out, gases can freeze back onto the surface. The air can thin. The whole system breathes on a timescale far longer than a human lifetime. New Horizons already suggested this living machine picture. Webb sharpens it. If haze particles are cooling the upper atmosphere, then seasonal chemistry is not just about what gases are present. It is about how those gases build particles that then rewrite the temperature profile. Temperature affects chemistry rates. Chemistry affects particle size and abundance. Particles affect cooling and radiation. Radiation and temperature affect what freezes, what escapes, and what stays aloft. That loop is why scientists are describing this as a climate system unlike anything else we have seen. Pluto is not copying Earth's playbook. It is running a different game with different pieces. And Charon is not just a spectator. Material can move between Pluto and Charon through escape and capture processes over time. Surface colors and compositions across the system hint at exchange and long-term processing. Pluto's dark tholins, those complex organic residues, are not random dirt. They are the end products of atmospheric chemistry raining down or accumulating through surface processing. When you look at Pluto's heart-shaped region, its rugged terrain, its layered hazes, and Charon's contrasting face, you are looking at a family of related environments shaped by cold physics and slow seasons. Webb does not replace New Horizons. It extends the conversation into wavelengths and thermal details that a fast flyby could not fully own. Now raise the stakes. Why should anyone on Earth care about a cold dwarf planet billions of miles away? Because Pluto is teaching us how atmospheres can work under extreme conditions. And extreme conditions are not just academic. Early Earth was not the same world we live on now. Its atmosphere evolved. Its chemistry changed. Organic hazes may have played roles in climate and photochemistry during certain ancient periods. Titan today is a natural laboratory for thick organic haze and complex nitrogen-methane chemistry. Pluto adds another reference point, colder and thinner, but still rich in organic particle physics. When Webb helps confirm that haze can dominate cooling and climate behavior on Pluto, It gives modelers a sharper tool. If your climate model cannot explain Pluto, maybe it is missing physics that also matter for other worlds, including ancient Earth scenarios or distant exoplanets with exotic particle-laden skies. This is one of the quiet revolutions in planetary science. We used to treat every world as a special case. Then we started realizing that the same building blocks rearrange into different climate architectures: greenhouse warming, anti-greenhouse effects, haze cooling, ice albedo feedbacks, escape of light gases, condensation of volatiles. Pluto sits at an extreme end of that spectrum, which makes it valuable. It stretches the models until they break, and then scientists rebuild them better. That is how discovery actually works. Not with a single dramatic announcement that ends the story, but with a result that forces the textbooks to grow a new paragraph. So what, exactly, did Webb change in plain language? Before we knew Pluto had haze, we suspected the haze mattered. Models already pointed toward cooling effects in some studies after New Horizons. What Webb adds is stronger observational leverage in the mid-infrared, a clearer confirmation of the haze's climate role, and a public scientific moment where the idea crystallizes. Pluto's atmosphere is not a fragile leftover. It is an active system with a unique thermal personality. That is why coverage talks about a new kind of climate. That phrase is not empty. It means Pluto does not map cleanly onto the familiar categories we use for other solar system atmospheres. Still, if you stop there, you miss the real shock. The real shock is how much remains unknown. Scientists still need better constraints on the exact composition of the haze particles. Are they simple organics, more complex macromolecules, layered particles with changing properties by altitude? How efficiently do they radiate at different wavelengths? How do particle sizes evolve through the atmosphere? How much of the cooling is direct particle radiation versus broader changes in energy transport? What about atmospheric escape? Pluto's gravity is weak compared with Earth's. Over long timescales, gases can leak into space. How does haze chemistry interact with escape rates? Does cooling change the structure of the upper atmosphere enough to alter loss processes? There are surface questions too. Pluto's nitrogen ice can flow like glaciers. Methane and carbon monoxide ices create complicated patterns of condensation and sublimation. If the atmosphere is thermally regulated by haze aloft, how does that couple back to surface ice cycles? Does it change frost patterns? Does it influence which ices dominate in different seasons? And what about possible subsurface processes? New Horizons left open debates about internal heat, past liquid water, and whether Pluto could have had a more active interior earlier in its history. Webb is not drilling into Pluto's crust. It cannot settle every interior mystery, but every time we refine the atmospheric story, we refine the boundary conditions for the whole world. Future observations matter. Webb can return to targets. Different instruments, different filters, different timing can catch Pluto under changing illumination and seasonal conditions. Ground-based telescopes and other space assets can add complementary data. Eventually, if humanity ever sends another mission into the Pluto system, whether an orbiter or a more advanced flyby architecture, the shopping list of questions will be much smarter because of Webb. That is how science compounds. One dataset does not close the book. It writes better questions in the margins. Let us also be honest about uncertainty and hype cycles. Social media thrives on absolute language. Everything changed. NASA was hiding something. A forbidden world. Those phrases get clicks. Real research is more careful and more interesting. The James Webb Space Telescope did not need a conspiracy to make Pluto fascinating. Stronger evidence for cooling by high-altitude haze is already a profound result. A climate system that does not match familiar solar system categories is already a profound result. Connections to early Earth atmospheric thinking and Titan chemistry are already profound. You do not need to invent a secret planet to make that story land. In fact, inventing one can weaken trust. The better approach is the one we are taking here. Separate verified findings from speculation. Celebrate what is solid. Stay curious about what is open. And Pluto's status as a dwarf planet since 2006 does not diminish any of this. If anything, it sharpens the irony. A reclassification that made Pluto sound lesser coincided with an era of discoveries that made Pluto look more complex than many full-size planets in terms of surface variety and atmospheric strangeness. Size is not destiny. Distance is not destiny. What matters is process. Pluto has process. seasonal volatile transport, organic haze production, thermal feedbacks, a binary relationship with charon, a place in the Kuiper belt where leftovers from solar system formation still preserve ancient clues. Webb's contribution is to show that even at the far edge, climate physics can be sophisticated. Picture the scene in your mind. Far beyond the warm inner planets, sunlight is weak, a pale trickle. Pluto's surface is a collage of ices, some bright, some stained dark by complex organics. Above that surface, a thin nitrogen atmosphere rises into space. Methane molecules drift through it, ultraviolet photons crack bonds, new molecules form, particles grow. A blue haze glimpsed by new horizons layers the sky. Those particles do not just float for show, they absorb, scatter, and radiate. They help set the temperature of the air. They help define what kind of world Pluto is. Webb, reading infrared light across immense distance, catches the thermal signature of that story. That is the human part. We built a telescope so sensitive that a haze on a dwarf planet can rewrite our climate intuition. There is also a humility lesson here. For decades, Pluto was a point of light. Then it was a blurry disk. Then it was a flyby world with maps and names and geology. Now it is a climate case study with mid-infrared constraints. Every stage made the previous stage look incomplete. That pattern will continue. The next generation of instruments will make today's conclusions look like a first draft. That is not failure. That is the method. If you love space because it feels final and settled, Pluto will frustrate you. If you love space because it keeps getting stranger under better light, Pluto will feel like home. So where does that leave the big curiosity gap we opened at the start? James Webb did change what we know about Pluto. Not by turning it into a cartoon secret, but by deepening the atmospheric story and strengthening the case that high-altitude haze helps drive its climate. That haze appears to cool the upper atmosphere. That cooling helps explain temperatures that once looked wrong. That process makes Pluto's climate unique in the solar system as we currently understand it. And that uniqueness feeds bigger science about how atmospheres evolve on cold worlds, how organic particles reshape energy balance, and how early Earth or Titan-like environments might be modeled more honestly. The Pluto-Charon system remains central to that story. You cannot fully understand Pluto as a lonely speck. It is part of a gravitational partnership, a seasonal machine, a chemical workshop at the frontier. When gases rise and freeze, when haze forms and settles, when ices migrate across the surface, the whole system participates. Webb's infrared eyes do not erase the beauty New Horizons gave us. They deepen it. They say the postcard was never the whole landscape. And yes, people will keep talking about hidden worlds near Pluto. The Kuiper belt almost guarantees more discoveries of small bodies over time. Surveys will find new objects. Orbits will be refined. Some claims will be real. Some will dissolve. That is normal. What should stay front and center is simpler and stronger. A dwarf planet once dismissed as a frozen leftover is now one of the most instructive climate laboratories we have. The shock is not that Pluto was secretly something else. The shock is that Pluto was always more than the story we told about it. If there is a final image to carry, make it this. Out in the dark, a small world runs a quiet engine. Sunlight is scarce, temperatures are brutal, and still, chemistry builds haze. Haze shapes temperature, temperature shapes climate, climate shapes the face of a world over seasons longer than a human life. Webb caught that engine's heat signature and forced us to update the map of what is possible. Pluto was never just a demotion debate. It was never just a flyby highlight reel. It is a living lesson in planetary physics, still unfinished, still surprising, and now brighter in infrared than it has ever been. That is what James Webb changed, not the romance of Pluto. The reality of Pluto, a small world with a working climate, a haze-driven identity, and a system that refuses to be boring. The edge of the solar system just got a lot more interesting, and the questions that remain may be the most valuable part of the discovery.